In today's video, we're going to be talking about the birth and the death of our solar system. And here we go. It's done. Did you see it? Welcome to What the Math. So yes, today's video is going to be focusing on the birth and the death of our solar system, and we're going to go back and, slow it down a little bit, and I'll explain to you how we think the solar system was formed today. So right there's a solar remnant flying around in this beautiful galaxy, but let's actually go back to this simulation called Supernova in the galaxy. I'm going to need to slow it down a little bit. And so what happened about 5 billion years ago, that's what we think at least, there was a huge supernova from a very large star that essentially exploded somewhere in the vicinity of our solar system. And this is of course before our solar system existed. And as it exploded and as this cloud expanded, it sort of combined into little chunks and created these little clouds called solar clusters or star clusters, and they're also known as baby star factories. And within those baby star factories, between 1,000 and 10,000 stars were actually formed simultaneously, and one of those stars was our sun. Now, it's kind of hard to imagine and hard to explain how this all occurred, but essentially because of the supernova, let me show it to you again. Because of this supernova right here, when it started pushing out the materials, some of it condensed into little chunks, and those chunks started to rotate faster and faster and faster, and eventually they kind of formed into, you can kind of see this similar effect happens right here in the galaxy itself. This sort of combined into this material that started orbiting around a central point, and there was obviously no black hole in the middle. It was just a kind of a central point where there was more mass, and eventually it sort of combined into what's known as protostar. So after a few million years, or possibly even less than, maybe after about 100,000 years, within that cloud factory, or sorry, star factory, or star cluster, one of those little chunks became this. It became a proto-sun. Now, it didn't really look exactly like this because it had a lot of stuff flying around it. So I'm gonna add a few rings to make it look a little bit more realistic. And really, it kind of looked more like this. So there was a central location where a lot of matter sort of accumulated and became very, very, very dense and relatively hot. But it wasn't really a star yet. This was still a protostar, which is why it's called proto-sun. And around it, we had a bunch of material, mixed material. Mostly, of course, it was hydrogen and helium. About 98% of it was hydrogen and helium, with the rest of the stuff being things like iron and silicates, and of course water and carbon dioxide. Now, the 2% material that was not hydrogen and helium was actually relatively new. It was formed because of the supernova, and essentially what supernovas usually do is, when one occurs, because of the energy released, it combines a lot of the smaller elements like hydrogen and helium into bigger elements, and eventually creates a lot of really complex molecules and atoms that we have today. But the oldest atoms, which are of course hydrogen and helium, were here from the beginning, from the Big Bang, and that's the stuff that is still in our sun today, and also on our Earth as well. We have some of the material that is still in our planet that is actually very, very, very ancient. So all of this occurred about 4.6 billion years ago, and this is where the star started to form. So as the material accumulated in the center, and as it kind of increased the mass of the sun, and we're going to do this manually, this is what really happened. So a lot of it started to kind of change orbits, and as the star became the actual star, as our sun became a sun, the material that was really light, so things like helium and hydrogen and even things like lithium, started to move on to the outer solar system, because sun has now started its nuclear reaction on the inside, and because of that, a lot of the things like solar flares and a lot of the solar wind that started projecting from the sun started to move the lighter material on the outskirts. So after a few 100,000 years, on the inside, we had a lot of the heavier materials. Things like iron, lead, and even things like uranium were all on the inside. And on the outside we had the lighter materials, and mostly this would be things like remainder hydrogen and remainder helium and any other light gases that just couldn't really stay on the inside of the solar system. Now let's increase the mass of the sun until it's actually similar to the actual sun, and we're going to do this manually right here. And what this basically created is what is known as a main sequence star. So Sun has now become a main sequence star. It's a star that has its own hydrostatic equilibrium, it has a nuclear reaction on the inside, and it produces a lot of heat and obviously a lot of light as well. All of this occurred within 50 million years after the initial supernova, and at this point our solar system started to be divided into little parts. Now, within about 4 astronomical units of the Sun, and that's of course, if I show it to you on the map, it's about 4 times the distance of Earth from the Sun. So here, where is our AU unit? So right about here. So this is the distance from the Sun. This is where only the heavier materials could actually become solid. So things like I mentioned before, silicates and iron and metals started to condense into little rocks. And this is the reason why we only have terrestrial planets in the center and not the gas giants, because of the heat generated by the Sun and because of all of the solar winds, things like Mercury started to appear because of, like in the previous video I showed you how this is actually made, because of all of the little rocks, little protoplanets. Let's actually put a few of them here. All of these protoplanets that were formed and being created near the central solar system started to collide, and let's wait for a collision to occur, and started to create larger and larger planets. In about 100 million years after the creation of the Sun, there were approximately 50 or maybe even 100 Mars-sized protoplanets flying close to the Sun, and this was all within about 4 astronomical units from the center. Now, because their orbits were a little bit more elliptical, the collisions occurred a lot more often than they are occurring right now. But within time, within hundreds of millions of years, most of these started to combine into larger and larger planets. And of course, this is how Mercury, Mars, Venus, and Earth were born. They were essentially the combination of various protoplanets that collided into each other and caused the formation of various planets. Now, I think a few of them actually have already collided into each other. And let's actually follow this Mars right here and see what happens to it after a few years. Well, let's accelerate this a little bit and wait for it to receive its guest. And so essentially many protoplanets combine into what we now know as 4 main protoplanets, or 4 main terrestrial planets, which are of course Mercury, Venus, Earth, and Mars. Well, we just passed by 2 Mercuries and not a single collision. That is some lucky Mars that I have here. So this is one Mars that is just doesn't want to combine with anybody. So let's actually do this manually. We're just going to throw a Mercury at it just because we want to have an explosion. And even though it's really lucky, not this time, Mars, not this time. Here you go. Here's your friend. So this is essentially how a lot of the planets formed. Now, this was in the inner solar system, and there's actually another part of the solar system that unfortunately didn't get as lucky. And the part of the system I'm talking about, of course, is right here. So you may not be able to see it very easily. It's actually not the best simulation to see it. But this asteroid field would have become another planet, or maybe even 2 planets, had it not been for the outer solar system. And let me just explain to you why and what happened and why it's kind of important. So on the border between Mars and Jupiter, there's a region where essentially various gases could now actually become gases. It wasn't hot enough for them, so they could start combining into chunks as well, and they could actually start accumulating just like the rocky and metal-y stuff did in the central solar system. And right on this border of Jupiter, actually, this is where many gases started to chunk as well. So what happened was something like this. So let's simulate the formation of the gas giants, and this is going to be a very basic simulation. So here we have the Sun in the middle, and on the outskirts, where it was cold enough for gases to form, something happened. So it's there's actually quite a lot of competing theories about what happened, but according to one of the theories, so a random terrestrial planet or some kind of a terrestrial object traveled to the outskirts and started to acquire a lot of the gases from this region. So the gases that were essentially chunking together and started to, and there's quite a lot of gases actually, hydrogen, helium, and a lot of other stuff that was flying around in this area. A lot of it started to basically fall or get attracted to this particular terrestrial planet. We're going to simulate this by actually going into materials and launching a lot of hydrogen toward this terrestrial planet. So a lot of it, as it flew past the sun, as it sort of orbited the sun, and the sun is actually somewhere right here, right? Where's the sun? There it is. There is our sun. So we're kind of far away from it. It started to acquire all of this gaseous stuff. Now, it could have happened completely differently, of course. It could have actually been just the gas itself that formed into a chunk, but it's more likely that there was actually a terrestrial planet involved, because we know that Jupiter, Saturn, and other gas giants do have a central core that is a terrestrial planet that's even more massive than Earth. Now, as it acquired more and more gas, it started to also spin just like the sun does right now, and this essentially what happened in the middle was this. So this gas giant started to kind of have a similar thing going as our proto-sun did. There was a bunch of material flying around it. In the center, there was a lot of hydrogen and helium and stuff like that, mostly hydrogen, of course. And on the outskirts, you had more gases, but also a lot of rocks and terrestrial stuff flying around, which eventually combined into this. And this, of course, is Saturn, but Jupiter was formed just in the same way, and Jupiter does have rings as well. So basically, all of this got combined into sort of like a miniature solar system, and of course, I'm talking about the formation of gas giants. And so we had a lot of various materials orbiting around them, and this is why the moons of Saturn and Jupiter have such a perfect circular orbit, because they were formed just when, or exactly the same time when Saturn was formed or Jupiter were formed. So all of these moons of Jupiter and Saturn, or other gas giants that have perfect circular orbits, had the same formation time as the Saturn and gas giants themselves. However, the other moons that you see flying around Saturn here, like these guys right here, all of these were captured asteroids or captured objects from the inner solar system, and obviously these were kind of acquired later on. But in the beginning, there was just this gas giant orbiting around the sun, and then it acquired all of its material by being just massive enough, and all of it started orbiting in this fashion and essentially created the gas giants. Now, Jupiter and Saturn were formed first, and then Neptune and Saturn were formed later. But what we don't understand about Neptune and Saturn is that they actually should have been a lot closer to the sun. So there's a theory called planetary migration theory that kind of says that it's very likely that many planets, including Earth and Mars and Mercury and, of course, Neptune and Uranus, have changed their orbits. They must have been in a completely different location around the sun initially, and because of the gravitational interaction, must have changed their orbits at some point. And because the stuff that the gas giants are made from is so abundant, these four guys, so specifically Jupiter, Saturn, Uranus, and Neptune, are actually about 99% of the entire extrasolar mass. So yes, Sun has the most mass, but the rest of the mass is in four of these extra large giants. So they're actually very massive, very big in comparison to anything else. The terrestrial planets, they are about 1% of the extrasolar mass, and they consist of mostly very rare things like iron, nickel, aluminum, and various silicates that are not as common in the universe as helium and hydrogen that these guys are made from. And so once Jupiter and Saturn were formed, because of their mass and because of their gravitational interaction, they actually prevented other terrestrial planets from forming. So because Jupiter was formed in such a close vicinity to the asteroid belt that's right here, you don't really see it, but it's actually right here. There's quite a lot of asteroids here. This is where Ceres and Vesta are as well. And because of Jupiter, it basically prevented anything else from forming. So a lot of these rocks ended up flying into the outer solar system. A lot of them probably became things like Ares and Sedna, which you see are flying somewhere over here, and possibly even Makemake. So all of these dwarf planets and all of these large asteroids probably came from the inner solar system, because Jupiter kind of kicked them out. I guess you could say they weren't really paying the rent and he kicked them out. Alright, that was a horrible joke. Let's not do that again. But of course, the inside of the solar system was kind of still active and things were still kind of colliding with each other. One of these collisions actually formed the moon, and I think I'll probably talk about this in one of the future videos, where Earth actually had a little visit from Mars-like object that ended up in us having a moon, and before that Earth didn't really have a moon at all. And so this is sort of the nutshell of how the solar system was made. Now, this is what we have today, and this is the solar system in modern times, but this is, of course, not the end. So, in the previous video, I talked about how it's very likely that in 3.5 billion years, we will have a collision with Andromeda galaxy, and this may actually cause some possible perturbations. Like, for example, if a large enough star passes by our solar system, this is what may happen. We're gonna launch a star that's about 6.7 masses of Sun at a velocity of about 70 kilometers going this way. It's going to pass relatively far at about 7 astronomical units away from the Sun. And let's see what happens to our solar system if that actually happens. Oh no, it disappeared. No! Oh no, it didn't. There it is. So let's see what happens. I'm kind of curious if this is going to seriously disturb our solar system, or if nothing will occur. So watch the orbits of various planets here. So we have Neptune and Uranus and Saturn right there. And here it comes, here it comes, here it comes. I think it actually passed by already. Yeah, it's gone. So, and look at that. Neptune flies away. So Uranus changes its orbit. Things just go wrong for our solar system. And even though it was relatively far from us, it will, or it has affected the orbits of other planets, and things just are not as cool as they used to be. And now let's look at Earth. That's the important part. Let's look at what happened to Earth and how it's doing in terms of temperature. So the temperature on Earth currently is, oh, actually it hasn't changed that much, but it is fluctuating a lot. It actually got a little bit cooler than before. It used to be 15 degrees, now it's about 13 degrees. So this is obviously not good for us, because if this occurs in whatever 3.5 billion years, things will very likely change for a lot of planets. Some of them might actually join the star that passes by, and some of them might fly away, just like Neptune did, fly away into the outer solar system and to never be seen again. But of course, this also may never occur. So what may happen, and what's very likely to happen, and actually will definitely happen, is that our sun will eventually, well, let me just show you this in a different simulation. We're going to look at stellar evolution of our sun. So our sun will very likely live out its life, and after a few billion years, start to expand and turn into a very, very large red giant. Now, unfortunately, this simulation has been changed, so it doesn't actually simulate this as well, but okay, yeah, that's not as exactly how it's going to happen. It's going to become a red giant very similar to a star called Antares, and that's actually what I just took, and I decreased its radius a little bit. And just for a comparison, this is actually the regular size sun. I'm gonna place it right here, and look at how massive it's going to be one day. It's going to be so large that it will actually swallow Earth and Mercury and Venus, and very, very likely also Mars. So this will happen at some point in the future, after about 4-ish billion years. And just for comparison, here is Earth orbiting all of this massive madness. So this is Earth, and look at how tiny it is in comparison to the future sun that is going to swallow this whole thing. Let's look at the chart just to give you a better perspective. We're actually going to zoom in right here. This is the red giant star known as the sun. This is the regular sun. And of course, right here, tiny speck. I can't even find it. Here you go. Here's Earth. Here is Earth. Anyway, so this is essentially what will very likely to occur to our sun. And as it's occurring, and as our sun actually grows larger and larger in size, but not in mass, of course, just in size and in temperature, the Earth will obviously start heating up as well. So interestingly, this is probably a very good opportunity for us to start, here we go, the slightly larger sun. This will be a very good opportunity for us to go into the outer solar system to satellites such as, or to moons such as Triton, Europa, and Ganymede, and actually start terraforming them, because the sun will actually provide a lot more heat to those outer solar system objects, but will actually probably blast our own planet with so much heat that everything here will be ridiculously hot. This will be over 100 degrees Celsius. Let me see if I can actually simulate this. And as the sun increases in size and as it becomes a bigger and bigger red giant, you can see the temperature is just jumping up. And this will actually only take a few million years for it to reach such a high temperature. So Earth will very likely be uninhabitable even before it gets swallowed by the sun. So this will actually occur within the next 4-ish billion years, and at some point the Earth will be hot and inhospitable to life. So we'll have to move our shenanigans somewhere else. We'll have to relocate and possibly move to the outer solar system. And you can see it's already smoking because it's getting hotter and hotter because of the sun. And this is not even that big yet. I'm going to increase the size even further just to kind of show you. Okay, no, that's not what I wanted, but okay. That also will happen at some point. So we'll basically get swallowed by the sun. And so once the sun lives out its life, and once it becomes a red giant, it will then undergo something called nova. Not supernova, but just nova. There's unfortunately no way to simulate this in the game yet, but basically it will release a lot of its mass, about half of its mass, as a kind of a solar wind that will, it will not actually be that dangerous. It will not kill anyone if it does happen. But a lot of its mass will fly into the outer system, and let's actually see if we can maybe possibly do this just using supernova. So it may kind of look like this, but it may also look completely different. We don't really know how to simulate this in the game here, or what it will look like in real life. But essentially, once the nova occurs, what you'll have in the middle is there will be something called a white dwarf. Now, the closest white dwarf that we are aware of is, of course, a star called Sirius B. I'm going to do something fun right now. I'm going to erase our sun and replace it with Sirius B from the list of stars right here. Here goes Sirius B. This is a star that is actually relatively comparable to the mass of our sun, but our sun will be a lot smaller than that. Our sun will be actually approximately 60% of this, maybe 55% of this, so it will be about half as massive as this. So this star is a white dwarf. Now, what is a white dwarf? It's a very dense star that has mass comparable to the sun, but its size is comparable to Earth. So if I were to add Earth right here, you'd see that it's actually about the same size. Now, obviously, this is a lot hotter, or too hot for us to actually be so close to it, but it doesn't produce enough heat. It doesn't produce enough radiation, even though it may produce enough radiation if we come closer to it. It will not be enough for Earth to stay warm. So Earth will start cooling down relatively fast after this, if it survives everything else, and will basically become a frozen chunk of ice. Now, because this is also a lot less massive than Sirius B, or our sun will actually be a lot less massive. Once the sun undergoes the nova, and once it becomes a white dwarf, this is what's going to happen. We're going to place Sirius B right here. It's very, very tiny because it's so small as a white dwarf, you can barely see it. And we're also going to change its mass to something a little bit more realistic. So it's going to be about 55% of the mass of sun. And so this is the white dwarf. I should probably just call it white dwarf sun. And ridiculously tiny right in the middle. Very, very bright, but only from a relatively close distance. Now, this is what solar system used to be like before the nova. Now watch what's going to happen within a few days. Okay, maybe a little bit more. And look at that. All of the planets, because there's no mass holding them closer to the solar system, will start flying apart. Some of them will obviously collide into each other. Some of them will do some other funny things, but most of them will change their orbits dramatically. Now, this will occur relatively quick, and it will take them quite a long time to reestablish stable orbits. And this is where a lot of collisions might start occurring, because a lot of the planets will start getting these elliptical orbits, which will often cause collisions. And so Earth now is totally uninhabitable. It's very cold, it's very, very, very dark, and on top of all that, it is probably going to collide with something. But here we go, we're gonna pass by the white dwarf. We didn't even see it because it's so tiny, and so you will not see it in the sky. You'll see a very tiny speck that will be the white dwarf, but unfortunately will not be enough to warm you up. So no more sunsets, no more sunrises, just very dark, very cold world. And so the sun will stay as this white dwarf for a very, very, very long time. White dwarfs are essentially, they consist of oxygen and carbon, and they are essentially the remainders that can kind of still burn a little bit, but they will not burn as hot, not burn as warm, and interestingly, they will be burning for a long time. The white dwarfs that have been generated from the beginning of the universe are still around, and most of them will still keep going for many billions of years. Our sun will probably live for at least 1 trillion years. That's quite a long time, actually. Unless, of course, it collides into something, or unless something called Big Crunch occurs. But if it stays as a white dwarf, it's going to be a white dwarf for a really ridiculously long time. And what will happen to a white dwarf after billions and trillions of years? Well, of course, it will become something called a black dwarf. Now, we don't actually have these yet. This is a very theoretical idea, but it will at some point become this. And this is actually the only simulation I could find that kind of shows you what a black dwarf looks like. So it will be a very dark, somewhat hot but not very hot object that will continuously have some sort of a burning reaction on the inside, but on the outside it will be completely dark and impossible to see. So this is kind of what a black dwarf looks like. Let me see if I can actually maybe run the simulation without causing the nova, and I think I can't. Yeah, there we go, there's a nova there. So yes, this is a very theoretical concept, but basically if I were to go into a new simulation, right here and just add a Series B, and then I'll just actually rename it into White Dwarf Earth to make it a little bit more realistic. Then we're going to disable realistic mode because otherwise it's going to supernova. And essentially, if we were to run this for many, many years, let's actually slow down a little bit and wait for it to start cooling down and live its life until it starts cooling down and getting a little bit less material on the inside, it will eventually become the black dwarf. So you can see it changing colors right now, and this is when it's going to become almost invisible. It's going to be very dim, very dark, very red, and at some point become completely black. And this is of course when at some point it might even solidify. We don't really know what's going to happen. It's all super theoretical, but it's definitely going to become this very large dark object after billions and trillions of years. By this time, of course, the solar system will have disintegrated because of its lack of its mass and because of the interaction with other stars. The solar objects like Earth and Venus and Jupiter and everything else will most likely fly into the outer solar system, and this object will be completely alone. It's going to be a lonely, dark object that will have no friends, no family, and it will be all by itself. Now, it's a very sad note, but this is unfortunately the reality of the future of our sun. Anyway, as I'm summarizing this, I just wanted to talk about something a little bit different. So I'm gonna go through this simulation again, starting with the proto-sun. This is a proto-sun, and up until the black dwarf. Now, I generally would not want to end the video on a sad note, but because we talked about birth and death of our solar system, and because today is a very important day for me, I wanted to end this on a somewhat serious note. Life is very fragile, and we all experience both birth and death at some point. Exactly a year ago, my mother passed away in her home in Canada without my knowledge or any warning, because she was a very strong woman and she didn't want anyone to know about her illness. Her strength and determination, just like the power of our sun, managed to propel me to the success in life that I currently have. She saved me from childhood trauma and from being a school dropout, and because of her, I was able to graduate from the top university in Canada. And although our relationship was not perfect, her selfless sacrifice and her death on September 27th will always remind me of how fragile our lives are. But at the same time, how one person's sacrifice can turn thousands of lives around and create something amazing. As this channel grows, I will always remember that if it wasn't for her, none of this would ever exist. Anyway, thank you so much to all of you for being amazing fans and for supporting me in creation of this channel. And whether you're in good or bad relations with your parents, I suggest that you think of going over to them and giving them a hug and maybe a little kiss or just thanking them. I love you guys and I love you too, Mom. Game you later and bye-bye.